Hello. Here is an example of solving a 2x2 system that is a system of equations in two variables with two equations. Okay, so we're going to use this using Gaussian elimination, which means using a matrix and elementary row operations to put the matrix in row echelon form, which we then convert back to a system of equations to solve. Just a quick reminder, row echelon form is when, for a 2x2, is when you have a 0 in the bottom corner, ones on the diagonals, and then anything else can be in the other spots. We don't care. And the same thing for a 3x3, which I will do another video to do an example of solving a 3x3 system with Gaussian elimination. That's the one where you've got ones on the main diagonal, and that's the main diagonal there, and zeros in the lower left-hand corner, and the other spots can be any numbers you want. So that's what row echelon form means. Okay, so let's do this system. So we start by writing the system of equations in an augmented matrix. So each row gets the coefficients from one of the equations. Remember, we use this vertical line here just to separate the coefficients of the variables on the left. So on the left here, we have the coefficients. And if you remember, the word coefficients refers to the number in front of the variable. And then on the right, we've got the constants, right? So the coefficients are on the left, and on the right here, we've got the constants. That means, right, the numbers without any variables next to them or being multiplied by them. All right, so I'm just going to erase this stuff. All right, so our first row has the numbers from the first equation, and our second row has the numbers from our second equation. Oh, wait a minute. Okay, so our goal is to get it in this matrix in row echelon form, so like that. So I always start with, well, unless the system is kind of weird, the lower left-hand corner. This person, these numbers are people. That position right there needs to be a 0. And we can't just make it a 0, right? We can't just multiply the row by 0 because that's not an elementary row operation, right? We have 3 row operations we can do. Let's see if I can summarize them with my own words. You can switch the equations if you want. If you want to interchange the equations, you can do that. That's one. You can multiply any row by a non-zero constant, right? Now the key, it's very important it's non-zero, because if you multiply something by 0, everything becomes 0, and then you don't even have an equation. And then the third one is you can replace a row by taking other rows and adding them together or adding multiples of them together. That's what you have to do to get a 0 there. You can add rows together just by lining them up and adding them together. So like, for instance, if I wanted to take the first row, I like to put the bar there even if I'm not in the matrix, just to remind myself, right? Like I could technically add these 2 rows together if I want. So I'd be like taking row 1 and adding it to row 2. But that would give me 5, 8 plus 6, 14, right? Which, sure, then I could put that as another row if I wanted, but that doesn't help me in any way. So I wouldn't just add them together as they are. What we want to do is multiply one or both. Sometimes you have to multiply both equations to get this to work, right? Oh, sorry. And sometimes, it's supposed to be black. And sometimes you only have to multiply one, but your goal is for the numbers in that first column to be opposites, right? So same number, opposite sign. So in this particular case, I think my pen is too thick. In this particular case, I noticed that on the bottom row, the first number is 10, which is already a multiple of 5, which is on the top row. That makes it easy because I don't have to multiply one row by something. So I also noticed that the signs are already different. The top row is negative, the bottom row is positive. That's great. So if I take row 1 and I multiply it by 2, and then I add that to row 2, right, I will get a row whose first number is 0, right? So I'm going to take that multiple of row 1 and add it to row 2 and use it to give me a new row 2. Okay, now I like to actually write it down. I know there's another video on here linked to one of those things where one of the questions where it doesn't write this work down, and I don't know how he does it. I got to write it down. So what I'm going to do is I'm going to write 2 times row 1 right here. That's going to give me 2 times -5 is -10. 2 times 8 is 16, and 2 times 3 is 6. Okay, and then I'm going to write row 2 underneath it, which is just 10, 6, and 5. Sometimes I like to remind myself that there's the augmented line, and then I'm going to add these two together. So -10 plus 10, there's the 0 we were going for. 16 plus 6 is 22, and 6 plus 5 is 11. Okay, so now that becomes our new row 2, right? That is now our new row 2. We're replacing row 2 with that. All right, so I'm going to come over here and I'm going to write that down. Whoa, what happened? Row 1 has not changed. Row 2 is now 0, 22, 11. Okay. Well, something I noticed right away is that row 2, all the numbers in row 2 are evenly divisible by 11. And so I would do that right now, just so I would have smaller numbers. I'm going to take that row 2 and, oh, I put S, looks like an S. Row 2 and divide it by 11, but I'm going to write it as multiplication. I'm going to multiply it by 1/11, which, as we know, is the same as dividing by 11. And that I'm just going to do that and then replace row 2 with that simpler row. Just the numbers are smaller. It's just nicer. You don't have to do that, but I definitely would. So I'm not going to write any work down for that because we're just dividing everything by 11. 0 divided by 11, still 0, right? 22 divided by 11 is 2, and 11 divided by 11 is 1. All right, so that's nice. Smaller numbers, I love it. And remember, that's totally legal because one of the elementary row operations is multiply a row by a non-zero constant. 1/11 is non-zero, so I just multiplied the second row by 1/11. All right, so we got the 0 in the corner, which is what we want. So what else do we need for row echelon form? We need, let's see, sometimes I just like to remind myself, this has to be a 1, this has to be a 1, and then that's it. Okay. So before I do anything to make this a 1, I think I'm going to do the work to make the -5 a 1. And it's actually really easy. So in this case, we don't have to add 2 rows together to get the 1 because we can make a 1 by just dividing the whole row by -5, which is legal, right? So here, this is what it looks like, right? If we take row 1 and we multiply it by -1/5. Now I'm using -1/5 so that it's a 1 and not a -1. And we use that to replace row 1. Notice how -5 divided by -5 is 1. So that's what it's going to work. Well, so that's not very much work. For some reason in my mind, I was thinking it was going to be more work. So we can actually do the same thing with the second row, but a different number, because we also want this number to be 1. So let's take row 2 and divide it by 2, which is the same as multiplying by 1/2, and replace that row with 1/2 times row 2. And that will give us 1s in both the spots. We need 1s for row echelon form. Okay. And this, hopefully we can all do in our heads. Hold on, So -5 times -1/5. What happened? -5 times -1/5 is 1. Now, -1/5 times 8 is -8 divided by 5, which is -8/5. Yes, not an integer, but that's okay. And then -1/5 times 3 is -3/5. Okay, and on the bottom row, 0 times 1/2 is 0, 2 times 1/2 is 1, and 1 times 1/2 is 1/2. All right, now we are in reduced, I keep saying reduced. Reduced row echelon form is actually a little bit more simplified, just in case you're wondering why I keep saying that. Reduced row echelon form is when you have the diagonal is all zeros, not zeros, ones, the diagonal is all ones, and everything else in this part is zeros, meaning so like this number would also be a 0. So you would have a 0 here and a 0 here and then ones here. That would be reduced row echelon form. And if you like the sound of that, feel free to do that. If you do that, your solutions are in the matrix. You don't have to do any back substituting. But we're going to stop at row echelon form and then come out of the matrix and write our system of equations that we now have, and then do back substituting to get the solutions. Okay, so each row of this matrix is now an equation. Maybe I'll write it over here just so we can see it. This first row tells us that x, 1 times x, which is x, minus 8/5 y equals -3/5. I'm hearing. And the second row is 0 times x, which means there's no x. We get y equals 1/2. So this is now an equivalent system to the system we started with. And so I might put a little curly bracket there. Notice how we already have one coordinate of our ordered pair, right? Remember that a system of 2 linear equations in 2 variables each is an ordered pair x comma y. Here we already know the y. Now we just need to back substitute that y into our other equation to get the x. All right, so let's do that. Maybe I'll do that in green. So we're going to get x times 8/5, not times, I said times, I didn't know why I said that, x minus 8/5 times 1/2, I think I was already in the times 1/2, equals -3/5. Okay, because what did we just do? We took this 1/2 and plugged it into that first equation. So that leaves x minus 8/5 times 1/2. Well, I noticed that 2 goes into 8 4 times. So that actually leaves 4/5 equals -3/5. And we're almost there. If we add 4/5 to both sides, x is going to be -3/5 plus 4/5, which is 4 minus 3/5, 1/5. Woohoo! Okay, so now we have the x and the y. So the solution to our original system, which I'm going to write down again for you here, just because it's all, I don't want to scroll all the way back up there. That system was -5x plus 8y equals 3 and 10x plus 6y equals 5. So the solution to the system is the ordered pair 1/5, -3/5. So that is our solution, right there. And that is the system that it's a solution for. Now remember, just to remind you one more time, what it means, right, to be a solution to a system of equations means that if I were to take this value for x and this value for y and plug them into each of these equations, x for x, y for y, that this one would check, it would be true, right? So the left-hand side would evaluate to 3, as is the right-hand side, and you do the same thing in the other equation, and it would also be true, right? So a solution to a system is a single ordered pair, right? And that single ordered pair is made up of 2 numbers, a single ordered pair that satisfies both equations in the system. All right, so hopefully that helps.